Yeah, thanks so much. Thanks everyone for coming. I'm happy to tell you about this work in collaboration with Jake Borgelli, Andrew McLeod, Matt Schwartz, and Christian Vergru. And my outline is written above, so I'm going to start with introducing the subject and motivating why we want to study sequential discontinuities. Then I'm going to go on to describe how we define sequential discontinuities in a useful way, which makes us able to relate them to cuts through the corresponding Feynman diagrams. Then I'll talk about in point 3 different cutting prescriptions, 2 different cutting prescriptions that we can use corresponding to different ways of taking discontinuities. And in one of these ways, we're going to see that it's important to know exactly which sheet we're on when we take these cuts and discontinuities. So that's going to be point 4, and I'll end with concluding. And please stop me at any point with questions. So as an introduction, we will consider and I will call them A. So we have some incoming particles, we have something happening, then we have some outgoing particles, and we are going to work with the magic Steinway variance. Which will be some sum over the external limit. Great. And in principle, we can calculate these as a sum over all Feynman diagrams. But even at 2 loops, this is challenging. So what we're going to do here instead is that we're going to leverage, instead of doing the full loop integrals, we're going to leverage the symmetries that we have on limits, such as the behavior of the amplitude in soft and collinear limits. And in particular here, we're going to be looking at leveraging analyticity to avoid doing the full loop calculations.
Doing the sum is challenging because it's many terms to sum, or because it's hard to do the integrals, or what?
Yeah, just because it's hard to do the integrals, right? As I say, even for some theories we don't know, or it's challenging to do them even at 2 loops. So let me elaborate on this point of analyticity. So Feynman integrals evaluate 2 functions, such as logs and polylogs, which are functions which have branch cuts. And to know which side of the branch cut we're on, we usually put all plus I epsilons in the propagators of our Feynman diagram. So let me show you an example of a diagram where it might be useful to not only look at one discontinuity, but to look at sequential discontinuities. So let me take my amplitude as this triangle diagram. Manual stems P1 squared, P2 squared, and P3 squared. And if we write the amplitude in terms of these variables, Z bar, then we find that the amplitude is, let's say, proportional to Li2 of Z, so the dialog of Z minus the dialog of Z bar, plus 1/2 log Z bar log 1 minus Z over 1 over Z bar. So what I want to show you here is that I want to focus on this first term of the amplitude, the dialogue. So the dialogue is a function that can be written as minus the integral from 0 to z, log of 1 minus s over s ds. So this function has a branch point at z equals 1, with a discontinuity across the branch cut at z equals 1 equal to 2 pi I times the log of z, meaning that if I draw this function in the convex plane, there will be a branch cut starting at z equals 1, which we conventionally take to go along the real axis. And if I take that function and I analytically continue it from right above the branch cut to right below the branch cut, the difference between the two functions will be 2 pi I times the log of z. But what I wanted to tell you is that the log of z now has a branch point at z equals 0 with a discontinuity equal to 2 pi I. This is pi I 2. So this is a branch point that you see after analytically continuing to the second sheet, or after taking one monodromy. You expose this branch point at z equals 0. Yeah.
So in going from going from the Mandelstam variables to C and C bar, there are also maybe some square roots, perhaps.
Yeah, there might be some square roots that we have to analyze, but actually, yeah, I'll go through a similar example in more detail later, and it ended up not being an issue. But you're totally right that in general, if we make these coordinate changes, then we'll have to be careful about that. Yeah, so if we take sequential discontinuities, this was the dialogue, and this is the log. If we take sequential discontinuities, we're able to probe branch points on different sheets, which absolutely appear in Feynman integrals. So let me keep motivating this by discussing some applications of this. Yeah.
Sorry, could you explain this a little bit more? I thought sequential discontinuities would be more than one variable, but here you just have one variable z.
Yeah, excellent.
So
Yeah.
first, well, let me not interrupt it.
Yeah.
Just recapitulate what you've done. You compare the answer on two different sheets, and that gave the logarithm. Discontinuity.
This is actually an excellent point that I'll go through in detail, because one of the motivations for us was that we wanted to be able to take sequential discontinuities in one variable sequentially. So I'll explain in detail how we construct that and relate that to cuts. But that was actually, yeah, one of the motivations to be able to explore branch points on different sheets in the same variable, in the same Mandelstam or here in Z. But you're right that previously, usually people had looked at sequential discontinuities in different variables. So the application of this is that generally we will want to use analyticity information. And I'm going to name two examples here that I'll come back to later in this talk. For example, transcendentality. And the Steinway relations, which I'll explain in detail later. To bootstrap amplitudes in perturbation theory. And I should also say that this has already, such constraints have already been used in n=4 super Yang-Mills theory to bootstrap amplitudes to high loop order. But one of the motivations for us was to extend these techniques to be applicable more broadly. So the ultimate goal is to apply these kind of analyticity constraints to bootstrap and fix the amplitude without having to do the full loop integrals as you would get from Feynman diagrams.
Could I ask a question?
Yeah.
Do you understand correctly that in this example, you took the discontinuity of the polylog function?
Yeah.
And then you analytically continued that, and then you took the discontinuity of the analytic continuation. That was the sequential discontinuity.
Yes, this is an excellent point that I'm glancing over here in a simple example, and that's actually the very next thing that I'm going to come to, how exactly I do this analytic continuation in order to take the sequential discontinuity. So thanks for bringing that up, and let me go on to that part if there are no further questions. By the way, can you read my handwriting? Is it big enough? Yeah, excellent. So let me go on to point 2. On discontinuities and cuts. So as I say, one of the goals is to generalize the traditional cutting rules. So let me remind you of those. If I have some Feynman diagram here in perturbation theory, I'm going to draw a 4-loop bubble for illustration. The discontinuity of this amplitude, according to the cutting rules, is computed by taking the amplitude, as I told you, with all plus I epsilons in the propagators and subtracting the amplitude with all minus I epsilons in the propagators. And this, according to the cutting rules, is equal to the sum over all cuts of the amplitude. So I'm going to draw one cut of this amplitude here for illustration, where a cut means that I take these particles that I've cut here, and I take the relevant propagator, which I'm here going to call K, and I replace it with a 2 pi I times the delta function in K squared minus M squared times a theta function requiring that the particle propagates with positive energy. And the hope is that the cut computation is easier than doing the full loop integral, and then we can probe the discontinuity without having to evaluate the function first. And now we want to generalize this. To sequential discontinuities. But how do we do that? There is actually a problem here with both generalizing the left-hand side and the right-hand side. So let me label this discussion as problems with the plus and minus I epsilon prescription for the purpose of generalizing the cutting rules. So first, as was pointed out, this discontinuity that I compute on the left-hand side is taken as the difference between the amplitude with plus I epsilons and minus I epsilons, and then I take epsilon to 0. So in my discontinuity expression, then I don't have any I epsilons floating around anymore. So I wouldn't a priori know how to insert them back in order to apply this formula sequentially. So the first problem is that the discontinuity is defined only on a line in the complex plane. So for example, if we take the discontinuity of a log squared of z, and we compute it as a log squared of z plus I epsilon minus log squared of z minus I epsilon, this is equal to 4 pi I times a theta function in minus z times a log of the absolute value of z. So this function is really only defined in this complex plane on the branch cut itself.
Sorry, before that, can I ask for the usual cutting rules?
Yeah.
What I epsilon prescription do you have to use on the right-hand side? Because there might still be loops.
Oh yeah, good. So there's plus I epsilon on the left-hand side and minus I epsilon on the right-hand side. That's a very thanks. Yeah, so as I said, it's not clear at all how to insert I epsilons back into this expression in order to be able to take sequential discontinuities. And again, if we want to relate sequential discontinuities to multiple cuts, how do we insert the plus and minus I epsilons into the cuts? Because if we have, let me draw again this picture, except let me do 2 cuts through that diagram. Then let's say I put plus I epsilons over here and minus I epsilons over here. Then the question is what goes in the middle, right? Or equivalently, if I start shuffling them around to different parts of the diagram, what should I put where? So the resolution to both of these problems is to define the discontinuity of the amplitude as, let me label it in the Mendel stem or variable S. Or let's say around S equals 0. As 1 minus the monodromy operator acting on the amplitude. It's supposed to be inside the right hand. Where M acting on A is analytically continuing the amplitude around S equals 0. And RS is going to be a region in the space of Mendel stems, which is going to be important later. But we're going to take it as the region where S is greater than 0, but all other Mendel stems are less than 0. So what this phi says is precisely that we're able to take sequential discontinuities by applying the monodromy operator sequentially. So now we get a handle on how to not put I epsilons in, but do this in a way that we can encircle branch points consecutively and define that as our discontinuity. Any questions before I go on to point 3?
Why is it that the cutting rules are somehow asymmetric in plus I epsilon and minus I epsilon? Like it seems like if I it doesn't seem symmetric if I swap I epsilon minus I epsilon.
Yeah, good. We'll actually see an expression later which resolves that. The asymmetry just comes from our way of writing it. There's a way to write it which is symmetric in plus or minus I epsilon. But then what you have to do is that you have to allow for multiple cut diagrams.
I guess it will be anti-symmetric in plus and minus.
Yeah.
Yeah, it depends on where you put the minus I epsilon. That's not very good.
But then there's also an asymmetry in the theta function for the energy. Those two things are correlated, right? Like in your example, it's really what makes it the amplitude times the complex conjugate of the amplitude. And so it's not just the epsilon that switches, there's also the theta of K0.
Right, but what I mean is that there is a way to write it down using multiple cuts where you don't have this apparent like asymmetry between the different cuts. Yeah. Well, you're right that the theta functions are not symmetric in taking particle factors, absolutely. So our third point is going to be how do we relate these discontinuities to cuts through the corresponding family diagrams? And as I told you in the introduction, we're actually going to explore 2 ways of doing that I'm going to call A and B. And these are going to be different cutting prescriptions. So of course, these are going to correspond to different types of taking discontinuities. So let me illustrate with a diagram what this will correspond to. Say we have some amplitude that has some branch points with some branch cuts attached to them. So in method A, what we're going to do is that we're going to rotate the energies, or external energies in the diagram, and basically see what we get. So we'll encircle some branch points in all corners. But in method B, what we're going to do is that we're going to encircle one branch point at a time. And there are advantages and disadvantages to each. So let me say A, what we do is that we're going to rotate the energies and encircle some branch points. While in B, we are going to solve the landau equations, which I'll talk about later. But the important part is that they find the location of these branch points, and then we will encircle one at a time.
Sorry, I'm a little bit confused by the picture because if you do A and you go to the first branch cut, you're on a different sheet, so you won't necessarily see that branch point, the second branch point.
Yeah,
right?
I guess
they're not all on the same
picture.
sheet. I mean, like there will be some.
Yeah, but you will see some branch
There will be
points.
some, yeah, you'll see something.
So my point is that as you take A, you will encircle some of them and you analyze which ones they are. But in part B, we really want to restrict ourselves to one at a time, and it's a good point that we will have to avoid all other branch cuts as we take this monodromy around B. Or the monodromy method B, I should say. And before I go on, I want to set the stage for where these are applicable. So A is applicable when the external particles are massive, but the internal can be massless, while B, because we're solving the landau equations, needs all particles to be massive. For now, but that's actually one of the things that we're trying to generalize to be able to apply to massless particles too.
Or B is just because you want to avoid these branch points colliding with each other.
Exactly. So we have to keep the particles massive, first of all, to avoid that. And in general, we want to keep the masses general even. So we don't get colliding branch points from like equal masses in our diagram. We want to resolve all of them as much as we can. Yeah, but the other problem is that the landau equations don't have solutions for the Feynman parameters or obvious solutions for the Feynman parameters as we take particles to be massless. And that's, I think, the origin of some of the problems where these relations don't seem to work so well for massless particles.
And in A, you're literally talking about energies, P0, right?
Yes. Which is actually a good point. That we're analytically continuing the energies and not the free momenta, which is why the external particles need to be massive, because if we start with massless particles, as soon as we start analytically continuing the energies, they become massive. So we can't restrict the mass to be anything. And in particular, we can't restrict the mass to be 0. All right, so let's recall the cutting rules that are still written over here. This is the first thing that we want to generalize. And as I told you, we have these methods A and B. There are a few proofs of the cutting rules, and we're going to use 2 of the proofs as an inspiration for how to generalize these. The proof that we want to generalize for part B is Kutkowski's proof. But in part A, we want to use the 't-Hooft-Veltman proof, which is very related to the proof in time order perturbation theory, to generalize with method A. So cutting rules can be generalized. using time order perturbation theory. TOPT for short. Which is also referred to as old-fashioned perturbation theory. So as a review, time order perturbation theory is an alternative way of computing Feynman diagrams, where the sum over all time order perturbation theory diagrams is equal to the Feynman diagram. But in time order perturbation theory, every single vertex is time ordered. So we actually get this to b factorial, where b is the number of vertices in the diagram. So for example, for the bubble, if I draw my Feynman diagram to be a bubble, then in time order perturbation theory, I would have to take into account both possible time orderings of the vertices. So here, for example, we have the possibility of 3 particles being spontaneously created out of the vacuum, 2 of which are later absorbed by the incoming particle. And one of the advantages that we're going to use is that in time order perturbation theory, all particles are on shell. So then you can see from the second diagram here that a feature of time order perturbation theory is that we don't have energy conservation at each vertex. And it's not Lorentz invariant diagram by diagram. And we also have b factorial of them for each Feynman diagram, which is why they're not particularly useful for So the Feynman rules are the rules for computing time order perturbation theory diagram. Let me illustrate it with the bubble, or that we integrate over the 3 momentum. And for each propagator, let me label the incoming particle as P, the loop momentum as K. For each propagator, we get 1/2 times the on-shell energy of the propagator. And then we get energy propagators, which are found by starting at the far left of the diagram, imagining a vertical line through the diagram here. And every time we cross a vertex, we write down 1/, the energy of the initial particle minus the on-shell energies of the particle that vertical line crosses. So here that would be the energy, the on-shell energy of P, minus omega K minus omega P minus K plus I epsilon. And now you can really see the advantage for the purpose of generalizing the cutting rules, because each cut in time order perturbation theory corresponds to 1 delta function, because it comes from replacing these energy propagators with delta functions. So here I would take 1/EP minus the sum of the omegas, and replace that with minus 2 pi I times the delta function in EP minus the sum of the omegas. So this is really a procedure that we can iterate. And this is much harder with Feynman diagrams, because depending on how many particles cross your cut, you have to put a different number of delta functions. And it's actually very hard to take the Feynman propagators and start expanding them in delta functions. It's really something that has to be done on a example by example basis, but here we can really keep taking those delta functions in sequence in order to get multiple cut diagrams. And we relate these two discontinuities by making sure that we're in the kinematic region where only certain cuts can be computed. So let me actually pre-written here. And you'll read this. So let me walk you through what I've pre-written here. These are the results that we proved using time order perturbation theory. So we have results for same channel discontinuities, meaning that we take monodromies in the same variable over and over again. And we take discontinuities by applying the monodromy operator around the zero of the Mandelstam that we're working in, or that we want to take the discontinuity in. So we apply that m times the amplitude in the region where only that Mandelstam is positive and all other are negative. And this is equal to the sum over all k cuts of the diagram, where k starts from the number of discontinuities that we're taking and goes up to the maximum number of cuts that we can take. And this CKM here is just a combinatorial factor coming from counting the different ways of getting these delta functions in time order perturbation theory. So C, I've written it here, is just a number as a function of K and M. It's related to the Stirling number of the second kind. And what we did here was that we computed this in a region R as 0, and where the plus denotes that we use all plus I epsilons. But again, we can rewrite it to have some minus I epsilons and incorporate some cuts, etc. It's not very important, but for practical purposes, it's nice to be able to just put all plus I epsilons in the propagator. Did you have a question?
Yeah, can you give an example of the cut of TOPT diagram?
Absolutely. So the cut of a TOPT diagram is precisely the same as in the traditional cutting rules. So you basically decide which are your incoming and outgoing particles, and then you do any vertical cut through the diagram.
But why do I get only one delta function?
Yeah, because I mean, so you start with a product of energy propagators, and you subtract the same product with minus I epsilons in the denominators. And if you resolve that into delta functions, you can write it as a sum over a delta function applied to each propagator with plus I epsilons on the left-hand side and minus I epsilons on the right-hand side. Yeah.
Well, I would have thought that if you are taking the mth discontinuity, you would have m cuts.
Yes, precisely. So this case starts at the number of discontinuities.
Why could it be bigger than?
Yeah, so the reason for that is that we're writing this with all plus I epsilons. So the way you can imagine, or the way that the proof works out, is that we have some propagators, if we apply this once, then we have some propagators with plus I epsilons and minus I epsilons. And then we rewrite the propagators with minus I epsilons as one with plus I epsilons and delta functions. So even like when I try to map this formula as written here onto the cutting rules, the traditional cutting rules, which would just correspond to taking one discontinuity and one cut, the way that I'm computing the right-hand side is that I'm still summing over multiple cut diagrams with all plus I epsilons. So you can do two things. You can do, for one discontinuity, you can take one cut through every diagram, and the price you pay is that you have to put pluses and minuses of I epsilons. Or you can sum over diagrams with all plus I epsilons, but then you have to sum over these multiple cut diagrams too. So as I say, the way that we wrote it here with this combinatorial factor is partially for practical purposes of calculating everything with plus I epsilons and not having different prescriptions floating around. And the example that I do here is that this is an example of a discontinuities squared in the P2 squared channel, meaning that I take two discontinuities in the P2 squared channel. Let's switch these here. Fix that. And the reason why I wanted to show you the full expression here is that recall that the ZZ bar variables are such that ZZ bar is equal to P2 squared over P1 squared. So you can kind of see hand-wavingly, although of course you'll have to compute it exactly, but you can see from this formula that minimally this logarithm squared of ZZ bar will contribute to the monodromy around P2 squared equals 0. And as I take two of them, actually these first two terms don't contribute, and the only term that contributes is this log squared. And the result is that I get a 2 pi I squared times the function in here. And we can compute that this is equal to 2 times the doubly cut diagram in the P2 squared channel. So this is actually the only diagram that contributes here because there is no other diagram that has 2 cuts in the P2 squared channel. So this is just to show you how these relations work out. We take two discontinuities of an amplitude that we know and we compare it with the doubly cut diagram. But of course, ultimately, we want to simplify our lives by only calculating the right-hand side if we don't know the full amplitude, and then use that information to get to the double discontinuity. So we also derived a formula for different channel discontinuities. Here I've written the one with only 2 for simplicity, but it's possible to generalize with these Stirling numbers to higher number of discontinuities. So the monodromies that we take are around those 2 branch points, or around those 2 contours around s equals 0 and t equals 0. And now what we have to do is that we have to sum over all possibilities of taking cuts in the s and the t channel. So let me show you an example of that. I hope this is still visible. So what we want to do is that with the yellow lines, we want to cut in the P1 squared channel and P2 squared channel. So those are the 2 corners here. And we start with summing over all 2 cuts. So those are these 4 diagrams here. Then we have to subtract the 3 cuts. Those are also 4 diagrams. And then add back the quadruple cut. Any questions before I go on?
Sorry, you gave an example at the beginning about dialogue, where you had branch points once at z equals 1 and then next at z equals 0. So there, again, for that, there is also a cut prescription.
Yeah, absolutely. And I mean, here I'm not, so in this example that I showed here, since I decided to take a discontinuity in P2 squared, it turns out that if you solve for the ZZ bar variables in terms of P2 squared, it doesn't, like as you rotate in P2 squared, you don't go around the branch point of the dialogue actually, in this case, but you could, if you encircle P1 squared or P3 squared, you will. And as you point out, the branch points there are at 1 and 0. So as we do these the continuations twice around 0, we'll pick up, first we'll pick up 1 and then we'll pick up 0. So we're agnostic to the exact location of the branch points, which as I say has advantages and disadvantages. The advantage is that we don't have to solve Landau equations to find them, but the disadvantage is that we don't get a handle on what each one looks like.
Can I ask about the case you just basically what Mary was just asking about again, just of the massive box? Say, so in the sort of usual way of thinking about it, the discontinuity of the discontinuity would be given by a quadruple cut, but that's off in the complex plane somewhere.
That's off in the complex plane, yeah.
So whereas everything that you're doing here in old-fashioned perturbation theory, everything is sort of real, on shell, positive energies, and so on. So how are those 2 facts related to each other?
I think what's going to end up happening, I mean, this is something that I'm very interested in generalizing to the possibility of encircling branch points that are often
a triple cut from here, I guess.
Yeah, so I think, no, I mean, I think in some cases, what we need to do is that we need to just adjust the kinematics so we can access those points in the physical region. But in other cases, if they really can't be accessed in the physical region, I still think that there should be such formulas. We just have to be more careful.
But I think, yeah, but I guess your formula and for the, I mean, we can certainly access the disk of the disk for the massive box.
Yeah, yeah.
The way that you're doing, but I guess your formula for that would not look like a quad cut, but would look like a triple cut.
Oh, yeah, yeah. In that case, yes, absolutely.
And there's some extra fact that triple cut by residue theorem is computed by a quadruple cut, but your formula would not give it as a quad cut, but
as a triple cut. That's precisely right.
Okay.
Yeah.
Thank you.
So as a corollary of these relations that are written down, and actually one of the motivations for using time order perturbation theory for us originally is that we have a new proof of the Steinway relations. So let me first explain what they are. Let's say I have an amplitude here with some Mendel stamps that I'm going to call S1, S2, and S3. And the Steinway relations say that the amplitude cannot have sequential discontinuities in partially overlapping channels. So for this particular example, the amplitude cannot have a term that looks like log S1, log S2, but it could have potentially a term that looks like log S1, log S3, because S1 and S3 are not overlapping. So our motivation for proving this in time order perturbation theory is that if you relate this to cuts, then the cuts would be overlapping. And that's something that doesn't occur in any time order perturbation theory diagram. But another thing that I should say is that these Steinway relations are used to bootstrap amplitudes in n equals 4. But this proof, of course, applies only when the external particles are massive. So one of the things that we want to do is that we want to try to extend this to be a proof for massless particles too. And there was an old proof in S matrix theory by Steinman. But here we have a proof that works diagram by diagram. So the proof by Steinman was only at the level of the full amplitude. All right, are there any more questions about this article? So let's see. We had method A and method B for generalizing the cutting rules. I think they were still here somewhere. So now we're done finishing, we're done exploring method A for a while, and we're going to explore method B. We don't want to limit ourselves to these energy rotations, but rather encircle one branch point at a time. So let me outline the steps to how we would find discontinuities and sequential discontinuities here. So the first step is to find the branch points using the landau equations. So I'm going to illustrate the landau equations with a diagram. Again, our two triangle. And I'm going to give every line here a Feynman parameter alpha and a momentum L. And the amplitude in this case is can be written as a d times L integral in the loop momentum, where d is the dimensions and L is the number of loops. This is the scalar integral here for the diagram that for, I guess, any propagators. So the Landau equations tell you where the amplitude might potentially have a branch point or a singularity. And we solve them by requiring that either the Feynman parameter alpha I is 0, or the particles are on shell for all I, and the sum over all loops alpha I Li is equal to 0, where this plus or minus depends on whether the L is along the loop momentum that we've assigned or the opposite. So now what we've done is that we've really pinpointed where in our space the branch points are. So that's step 1. Step 2 is to compute the monodromy around these branch points. And we can do that using Kutkowski's formula. So 1 minus the monodromy operator around the branch points. Let me label the variety with the same notation as in our paper. So I'm taking the monodromy around a variety defined by phi 0 equals 0, where phi 0 is some function of the mental steps. And this is computed by putting particles on a shell. So it's a product. Let me actually try to write it on the next board.
Is it obvious that the solutions of landau equations, so demanding that there is a solution implies that you're in codimension 1 place in the space of Feynman?
No, not at all. So this is restricted to codimension 1 branch points. That's a great question. So for codimension 2 branch points, we can sometimes like resolve them into products of or sequential codimension 1 branch points, but sometimes we cannot.
Is there an example of a situation where there's a genuine, honest, just codimension 2 branch point that doesn't arise as the intersection of 2 codimension 1?
Yes. The one you sent us, Sebastian, right?
Oh, the ACK node one, right?
Yes.
Yeah, right. The infamous ACK node, right.
Is that statement only true for real values? If you let everything be complex, I don't know if it's so true.
Yeah, so here, the way we're doing it right now, we're always restricting ourselves to the physical region. But as I said before, like we're very interested in generalizing it to be able to encircle branch points that are somewhere off in the complex plane.
I know, but that's not precisely what I meant.
Yeah.
One's question had to do with whether these equations lead to a singularity in codimension bigger than 1.
Oh, yeah.
And you said yes.
Yeah.
Well, I wondered, had you regarded the variables as complex variables, if you still would have made that statement.
How do I, sorry?
If the variables are taken as complex variables, I wonder if it is the case that singularities are always in complex codimension 1.
Oh, I'm not sure, to be honest. That's a good question.
So sorry, in particular, you're asking that the solutions that you're finding here have all real positive alpha. Is that right? Or no?
Yes, for now I am. But as I say, I think, yeah, I definitely think it can be generalized, but for now we're restricting ourselves to the case where we know how to solve it. But
It's that case for which restricting to that, where the first singularity you find could be in codimension 2, funny example. Is that right?
I wouldn't think that arises for positive alphas. And another thing that I wanted to say is that like this monodromy formula, as I'm going to write it down, it requires positive alphas. But the way we find where the branch points are, that does not require positive alphas. So actually this point 1 is going to be general, point 2 is not going to be general for non-positive alphas for now, but point 3 is again going to be general for any alphas. Right, so this monodromy is equal to the cut integral. This is Karkowski's formula. So for the alphas that are not 0, I cut the propagators. But for the alphas that are 0, I keep the propagators intact. And note that I've not written yet here what this monodromy operator acts on. So in our most recent paper, we were interested in precisely what we should put in this bracket here. And the reason is that this formula gives us the monodromy around a branch point, but it doesn't tell us on which sheet that branch point is, or how many monodromies we've taken already of our amplitude to get to a sheet where we can encircle this branch point here. So I'm just going to sketch an argument for where this branch point is, not go through the proof. So what we do is that we Feynman parameterize and expand our amplitude around this branch point. And what we get is that the leading non-analytic behavior of the amplitude is a constant as a function of phi naught times phi naught to the gamma, define gamma in a moment, times log phi naught to the gamma times a log of phi naught if gamma is a positive integer of 0, or a constant times phi naught to the gamma otherwise. And gamma here is loops times dimension times number of non-zero Feynman parameters alpha minus 1 over 2. And then we can figure out what sheet this is on polylogarithmic functions. And I'm going to illustrate this with the Li of gamma plus 1, which has the expansion phi naught to the gamma log of phi naught. This expansion is actually more general than for the Li. It's for all polylogarithmic functions. For generalized polylogarithmic functions, we get that phi naught is on the gamma plus first. And this actually gives us a bound on the transcendentality of polylogarithmic finite integrals, because the maximum is obtained when n in that gamma formula on the far right board is equal to 1. So the maximum is LD minus 1 over 2 plus 1, which is the floor function of LD over 2. So this is a bound that's actually used in n equals 4, or conjectured and used in n equals 4. Here we have a proof of it, but again, we require all the particles to be massive in our diagram.
And you've assumed that the answer is polylogarithmic to get a
We
bound
assume
on
that the
it.
answer is polylogarithmic, yes. And for those of you who are familiar with the symbol, this also tells you where in the symbol this singularity occurs. It occurs in the gamma plus first entry. So that concludes what I wanted to say. So let me summarize all of it in point 5. What we did was that we looked at how to define discontinuities in a way that would be where we could generalize it to sequential discontinuities. And then we had 2 ways of relating them to cuts. So we had 2 different cutting prescriptions that are written here. In A, we did an energy rotation and proved some relations using time order perturbation theory. While in B, we found the location of the branch points using landau equations and encircled one at a time. And the last thing I did here was that I sketched how to find which sheets these branch points are on, because we already know how to calculate their monodromies with Kutkowski's formula, but a priori we didn't know where they were located or how many analytic continuations we would have needed to do in order to see them. So that was the last part here about finding the gamma and finding which sheet the branch point is on. So thanks everyone, and I'm happy to take more questions.
Questions?
Kind of a basic question.
Yeah.
So the first picture for the discontinuities with cuts using more perturbation.
Yeah.
It looks like it would. I mean, naively, it looks like you keep taking this, you keep cutting, and eventually you should run out.
Yeah.
But don't we know that that's not true? Like for like elliptic functions or whatever, aren't there cases where I mean, when it's polylogarithmic, we can keep taking this and eventually we run out. But I thought that we don't know in general if that's true. I thought elliptic functions don't.
Okay, yeah, good. So this would be a bound on the discontinuities as we take starting from this region, starting from the positive region, and encircling, basically taking an energy rotation so that the energies that the propagators can go on shell just barely go on shell, so we don't allow ourselves to go up in the complex plane. I think method B that I presented will be easier to generalize to branch points in the complex plane, and there we definitely, as you said, find that.
I think it's just so that the kind of the portal to the kind of infinite world of you're not seeing, you're not
exactly. It's restricted to these discontinuities starting in the region where the Mandel stems are positive that you want to take a discontinuity in, and then you analytically continue to the Euclidean region and back, basically.
I have a question about that number 3. So you said the amplitude behaves like those powers of power. But I'm confused because naively, if I look at that and I ask what's the discontinuity around 0, we can get some contribution from the lower, just in the first branch.
Yeah, that's a great point. So the operations don't commute. It doesn't commute to take a discontinuity and then expand in phi 0, or expand in phi 0 and then take a discontinuity. So this is an expansion around phi 0 equals 0.
I would think for the purposes of taking the discontinuity around phi 0, it should commute. You say it doesn't commute?
No, it doesn't. In simple examples even. It doesn't commute.
Well, if there are no more questions, let's thank Hofi again for